So the first one we'll look at is question 8. And those of you who had a chance to look at this figured out something that is actually really one of the few things about this book that really gets me. One thing is the variables, the way that their notation. I don't like that. The other thing is that they have 2 sections at the end of each chapter. One is called questions, one is called problems. The questions tend to be more sort of multiple choicey, but not universally. And the problems tend to be more like story problem-ish, but again, not universally. The thing that they did that's such a huge mistake is they started the numbering over. So if you say, can you do number 5? I don't know whether you're asking about question number 5 or problem number 5. So my notation is just this. When it's one of the questions, I'll put a Q. When it's one of the problems, I'll put a P. Those 2 sections are labeled questions and problems. And since none of this is required and you don't get points and all that good stuff, if you accidentally do a question when it should have been a problem or the other way around, it's not the end of the world. So question 8 says, a ball is thrown straight up in the air. So here we have a person, and I'm going to take a second and draw a realistic person here, because I think it's important for you to know who we're looking at. I was in a band for years, by the way, and our name, which I thought was awesome, was the Stig Band. Isn't that a great name for a band? We were a good band.
What kind of band was it though?
It was an old person band. At the time, we weren't old, but now it's old person music.
Like what?
Does that make any sense?
Kind of old?
It's kind of like when Elvis was young, that music blew people's minds with its like edginess.
Right.
And now you're like, okay, grandma. So that's why, like, it's all good though. All right, so ball straight up in the air. At which of the following instance is the ball's acceleration equal to g, negative g, 0, less than g, or greater than g? And that begs the question, what the heck is g? And the answer is, the way to find this stuff is to like look through the chapter. And I said in the homework, read chapter 2. That doesn't mean study chapter 2, learn chapter 2. That means glance through chapter 2, and then when you get to a problem like this and you're like, gee, what the heck is that? Then you'll remember, oh yeah, I remember it says g when they're talking about free fall, and it talks about the fact that g is always positive 9.8. G is positive 9.8 meters per second squared. The positive has nothing to do with direction. G is a constant that is defined as the magnitude of an object's downward acceleration close to the Earth. So it's not negative, even though if you were to have a frame of reference in which down is negative, an object's acceleration will be negative when it's in free fall. G is always the number positive 9.8. Okay, meters per second squared. So that means that anything in free fall, when you have a reference frame in which up is positive, will always have an acceleration of negative g, or negative 9.8 meters per second squared. And the question is asking about a bunch of different time periods. So one is just after leaving your hand. Just after leaving your hand, it's in free fall. It will have an acceleration equal to negative g. At the very top of its motion, it's still in free fall. It will have an acceleration equal to negative g. And just before hitting the ground, it is still in free fall. It will have an acceleration of negative g. So the entire time this ball is unsupported in the Earth's gravitational field, it will have an acceleration equal to negative g, which is negative 9.8 meters per second squared. This is the kind of thing that, like, this is arbitrary. They didn't have to say that g is always a positive number, but they did, and that means that our acceleration is going to be negative g when our frame of reference says that up is positive. Okay. So, all right, so that's number, whatever that was, 8. Number 9 we can think about in a few different ways. So number 9, the question says, there's somebody standing on the balcony of a building, and she throws 2 balls. One she throws straight down, and one she throws straight up. She throws them with the same speed, just in different directions. And then there's an observer a couple of stories below. And the question is, as those balls go past the observer, how will their speeds compare? Okay, so we know that they're not going to go by the observer at the same time. One is going to go up first and then come down. The other is just going to come straight down. So one of those will show up first, but that one will go by, and the other one will go by. How will their speeds compare? There's a bunch of different ways to solve this problem. The way that I always recommend that people think about these problems whenever it's possible is to use that framework I gave you the other day. So you draw a picture, you establish a frame of reference. I said, wherever that observer is, that's our position 0. Because we can put position 0 wherever we want. I said up is positive. We don't know how far up above the observer the person who throws those two balls is, but whatever distance that is, they both have the same starting place. So I just called it y. And then I went through and I did a variable inventory, and it turns out for both of these objects, they start at position y. As they're moving past the observer, they're at position 0. Their initial velocities are the same in magnitude but opposite in direction. So I just said, well, whatever that is, it's v, that magnitude. So one has a magnitude of v in the positive direction. The other has a magnitude of v in the negative direction. We don't know the final velocity for either one of them. That's what we're trying to find out. They're both in free fall the entire time. So they have an acceleration of negative 9.8 meters per second squared, negative g. And if you look at our equations, we have one that relates our 4 knowns to our unknown. And that's this equation right here. This equation has some squares in it. We're squaring the initial velocity, which means the fact that this one has a negative and this one has a positive initial velocity of the same magnitude won't matter. They will both have the same squared velocity. Negative 5 times negative 5 is the same as positive 5 times positive 5. To find the answer, we have to take the square root. The square root of whatever we got here could be a positive number or a negative number, but we know in this problem they're both going down. So we know that both of those velocities are going to be negative. The magnitude of this number is going to be the same. This number is negative 9.8. This number is going to be the same for both objects. They will have the same final velocity, and they pass this point. One gets thrown up and then comes back down. One gets thrown down. They'll both have the same velocity once they go past this point, right? So that is number 9. And then the next one is the flea. And the flea is, the complexity of this problem has to do with the fact that you have to make some assumptions about what's going on here. Because if you think about what's actually going on, we can't deal with the problem without making a few assumptions. Because what the problem describes is a flea that's jumping off the ground. And over the course of its jump, it moves. It moves by 0.5 millimeters. Well, what does that mean? What does it mean for something to move? If I move a meter to the right, then that's like this, right? Like I've just moved a meter to the right. But what if only part of me moves? What if I do this? Now how much did I move? Some of me moved more than a meter. Some of me hardly moved at all. Some of me kind of moved in the middle. How do you deal with that? With a flea, in order for it to jump, its legs have to stay in contact with the ground while they extend. So part of its leg, its foot, is on the ground the whole time. Part of its leg is extending, and its body is what rises 0.5 millimeters. So how do we solve this problem? We're just going to make the assumption that somehow the entire flea, legs and all, is what we're really tracking, even though we know that part of the flea has to be in contact with the ground to provide that needed acceleration. We're just going to pretend like those legs don't have any mass, effectively. We're going to pretend like the legs are just like invisible propulsion systems that don't really change the location of the flea at all. And so that means that we know that the initial position of the flea is the ground. Let's call that 0. The final position of the flea is 0.5 millimeter above the ground. We're told that once it has launched, it has a velocity of 1 meter per second. So that's at the moment its feet are no longer touching the ground. And then we have some knowns, and we have one unknown, which is the acceleration. We use actually the same equation that we just used to find that. We can solve for acceleration if we know initial and final velocity, initial and final position, and we know that the acceleration was constant, which we do. Yeah?
Are we expecting to have all of these equations memorized?
No, even on the AP exam, they give them to you. You will have this sheet or something very much like it with all the equations on it. Yeah. Okay, last one is problem 33, and this one is I think if I remember correctly, I haven't done this one in a year, but I think that I think this is basically the same problem as the fleet. Okay, so for this one, we have a cross-country skier. She is zipping along. She's zipping along at 8 meters per second, all right? And then she slows down until she is zipping along at 5 meters per second. That motion happens over a distance of 5 meters. Okay? And the question is, what is her acceleration? In fact, the question is, what is the magnitude of her acceleration? We'll come back to that in just a second. So the magnitude of her acceleration is what we're trying to find. So let's follow our rules. We're going to say that this is position 0. We're going to say that to the right is the positive direction. So our variables are going to be initial and final position, initial and final velocity, acceleration, and amount of time. We don't know how much time it took. We don't know the acceleration. That's what we're trying to find. The initial position is 0. The final position is 5 meters. The initial velocity is 8 meters per second. The final velocity is 5 meters per second. Same equation will help us find the acceleration. The acceleration is going to be equal to the difference in the squares of the velocities divided by 2 times the displacement. And you don't have to memorize that. I don't have that memorized either. I only was able to write that because I wrote this morning. And lest you think that I have confidence, I just flipped back to this to show you that I did this morning and also to check, because it's very common for me to write equations wrong if it's not like a standard equation that I use all the time. But that looks right, so I think I got it there too. I'm not going to plug the numbers in because you can do that on your calculator. It's going to be 5 squared minus 8 squared divided by 2 times 5. And what you end up getting is a negative number, negative acceleration. If you have a positive velocity that becomes less positive, you're slowing down. The acceleration in that case is going to be negative. Positive velocity with negative acceleration means you're slowing down. The question is asking about the magnitude. So in this class, labs, and when I'm talking to you about stuff, I'm never going to try to trick you with things like that. I'm never going to ask you for magnitude and then punish you when you accidentally include direction. But I can't guarantee that that's going to happen on the AP exam. I don't think they're going to do something like this because it would be jerky. But they are jerky. They're all terrible individuals, and so they're trying to make you miserable. So just keep in mind that when you're asked for the magnitude of something, it means the size with no regard to direction. So in this case, the correct answer to this problem is a positive number, reflecting the magnitude of the negative acceleration in this case. All right, and that is that.